Thanks for the introduction. So my talk is on spectrum consumption models, and I hope you find it interesting. So basically, besides my academic position, I'm also a member of the one of the IEEE standardization committees on dynamic spectrum access networks, the 1905 standardization work group on standardization. And as part of that work group, we've been working on developing spectrum consumption models for quite some time. But usual disclaimer, all the views and comments in the talk are only my own, not those of the IEEE or its standardization committees. So basically, one of the problems we wanted to address within IEEE was to find a way to a common means to define a spectrum use and define the boundaries of spectrum used by any type of radio frequency device or spectrum dependent system. We were lucky around 2012 that engineers from the MITRE Corporation had also been looking at this quite extensively, and they brought some of the work into IEEE for standardization, and then we just started developing around it with other members of the academic, industrial, and scientific community. A lot of input from DoD, I should say, by the way. So the idea is to define a data model that clearly defines the boundaries of spectrum use, helps us identify how a system emits electromagnetic radiation, what's interference to a system, and if it's a very common and well understood model, it will allow different types of participants in the wireless communication ecosystem to collaborate with each other and enhance spectrum sharing and wireless services. So I'm taking a note from systems design theory. We approach the design of these data models as a loose coupler. So in systems design, a loose coupler is an element that allows innovation on either side of its use. So think about it as the IP protocol and networks. That's a loose coupler. Think about it as the interface for your power outlet. So 110 volts, 60 hertz, and that's it. So no matter where that power gets generated, so nuclear, wind, solar, as long as it gets to that outlet at that time with those characteristics, that energy can be used. And on the other side, you can plug a computer, a toaster, a refrigerator. You can plug whatever you want, and you've got innovation on that side too. So the idea here is to develop a loose coupler in the spectrum management field. So it would be a data model that allows a wide diversity of spectrum management methods and regimes to be enabled on top of it, and a whole diversity of spectrum uses and devices, frequency hopping, direct sequence spread spectrum communications and such, to be specified and also expressed within an SCM. So again, one of the key goals, provide a means to capture all the relevant parameters and phenomena that affect spectrum consumption. So any device that uses spectrum, whether as a transmitter or as a receiver, we assume it's consuming spectrum. One key item also, which came early on in the design of these models, is to provide a means to compute compatibility between any two models without, and that's the key word there, dependence on external databases of environmental or system data. So the idea is that if if transmitters from NADA need to verify compatibility, by compatibility, by the way, we mean that not causing interference to others. So that's what we mean by compatible. Two systems are compatible if they're not causing interference, that hinders their operations. Obviously, there will be interference, but the point is that it doesn't hinder their operations. It's still within the tolerable limits that they express in their models. So as we have the models, we also in the standard we also put in the let's say the procedures, algorithms, if you want to call them that way, to use the information in the models to perform this compatibility computation. And since it's a standardized computation, let's say two entities won't get into a fight saying, well, my calculations say you are interfering, and the other guy says, no, my calculation says I'm not interfering with you. So if we have everything in one single standard, one single common piece of information to make these judgments, we avoid a lot of issues. So the objectives of the standard, kind of mentioned them already, define the data models. So the data model elements that go into SCM, we call them the constructs. And then those high-level constructs have a lot of elements inside. The standard defines the procedures to arbitrate compatibility. And it also provides a means to generate machine-readable SCM. So the idea is to automate as much as we can spectrum management processes with the information being captured in these data models. And we expect that this will help in the W techniques, new processes, algorithms to dynamically coordinate spectrum access. So the first version, well, the current version of the standard, I should say, was released at the end of 2017. It's the 1900.5.2 standard. And the official version actually went to the public. So this is what the IEEE actually got released to the public May, June of 2018. So that's when you could buy it if you were looking into this. After that, public release, we've been getting, by we being the standardization committee, has been getting input from mostly industry and DoD on a few enhancements to the first version of the standard, which basically are just enhancements to, let's say, take into account some special cases that might be of interest. And also we're taking the opportunity to also standardize methods to formalize a little bit more the way spectrum concentration models can be represented and exchanged. So this is what goes into a spectrum consumption model. It's 11 constructs, right? And these are the names, and these are the main issues, their main uses. Some of these constructs are mandatory for a transmitter model. Some of them are mandatory for a receiver model. Some of them are optional. The ones that are always optional, regardless, are the ones in italic. But all the other ones, again, depending on the case, transmitter, receiver, or other types of systems, they're mandatory. What I should mention is that most of these constructs also include a way to capture probability within them. So you're not just married to one value of the construct. You can specify a range of values and associated probabilities with getting to an operation within that value, so that we're not always planning within a static set of values. So in the next set of slides, I'm going to quickly go over some of these elements, and then I hope to finish the presentation with some potential uses and use cases, and some of the things that we're doing with SCMs in the context of the IRIS Center proposal. By the way, I should mention that one of the demos at the end of today's session shows an example of an interaction between different radio devices using SCM. So if I hope you stay up for that demo. So one first thing about SCMs is that we have the constructs. The constructs can be used to build what we call a transmitter model or a receiver model. These transmitter and receiver models can then be aggregated into what we call a system model. And then these system models can be then also aggregated in what we call a set model. And you could use these combinations for many different things. The interesting thing when you start going into this hierarchy is that if you want to verify, so for system and set models, you have what we call an Uber model that captures the whole, let's say, bandwidth occupation of all the transmitters in the system. It captures all the common parameters of all the transmitters in the system. And if you manage to be compatible with the the top Uber model, then you don't need to do compatibility computation against every single SEM in the system or the set. But if you're not compatible with the top model, then you do have to go and scan which transmitters or receiver inside the collection is the one that's causing you to not be compatible. Another use is that for a specific case of set models is that there's a specification in the standard where you can tailor their let's say usability or operation as a authorization set or as a constraint set. Basically, what this means is that you can build an SCM that that devices can interpret as a permission set where they can operate, or as a set of transmitter receiver models where they cannot operate. So basically telling them you cannot transmit it in these frequencies at these times and these locations and things like that, or the vice versa of that. It would be the authorization set saying you can operate in a given set of conditions and locations. So how are models built? Basically, it requires a radio engineer to have extensive knowledge of the system being modeled and capture the details of that system and put them into the appropriate values within the appropriate constructs in the NSCM. So things that need to be known and modeled are how much power does the system emit? How does it emit it? What's the spectral mask? What are the propagation conditions, the attenuation coefficients, all of this in the area of operation of the device, and what are the characteristics of the receivers that you want to model, what are the filtering, right? So all of those parameters need to be analyzed, processed, well known, and then you can put the right content and the right values in this. Yeah. So modeling is an art. There's not really a specific algorithm for us to tell you how to model your device into an SCM. You really have to understand well your device. But at the end, the SCM will be an abstraction that again does not require detailed data and computations that had to be used in the production or in the finding of the values that have to go in the SCM. It has to be one self-contained model with which hopefully you approve of. So in terms of the constructs, I'll just explain a couple of more important ones just for the sake of time. So one's the reference power. So this is a reference value to which other model constructs refer. So basically, you can think about it as the total energy emission from a device, and then this energy emission is then spread out as specified later on in a spectrum mask. The spectrum mask, this applies for the receiver, so people are very familiar with these, right? So you specify frequency and energy level values with a given resolution bandwidth. And there are a couple of ways that you can, let's say, introduce these values into an SCM, with mentioning actual frequencies or mentioning relative frequencies. But basically, as it says here, it conveys the spectral density of power as emitted by a device. An underlay mask is a list of inflection points, but we call them now control points, that that indicate what is the allowable interference for a receiver. So it specifies, specifies a limit to the allowed interference by frequency for a receiver device. Power map, it conveys the dispersion of electromagnetic energy. So this is the antenna radiation pattern. That's basically it. So it specifies the relative power density by direction as it comes out from the antenna, right? So you can model directional antennas, omnidirectional antennas, and that this is the limit in that sense. So it provides a directional gauge. So I just have to pause here because That's an important point. So when you have the reference power level, the spectrum mask, or the underlay mask, depending on, let's assume it's a transmitter. So the reference power level, the spectrum mask, and your antenna radiation pattern or power map. With those three values, you can compute the power spectral flux density at the 1 meter point, and then you use that value for the remaining computations that you need to do when using SEMs to compute compatibility. Okay, so I just wanted to specify that. So then you have a propagation map that so there's a construct to capture how in the environment where a device might be placed, how the environmental the environment in that location may impact propagation. So it assigns parameters of path loss, modeled solid angles about a point. And there are a couple of models. They're not only two now. You can support, they're all log distance based, but you can support more than two. So again, just to provide a bit more detail, so this is a log distance path loss model. It's piecewise linear. We don't incorporate shadowing or fading effects because that's that would be probabilistic. Again, as I mentioned later, the intent of the models are to protect devices, not to do predictions. But if you did want to include some probabilistic effects, you can do that by incorporating several families of these path loss models and say, I think this will be a path loss model at this probability, at this other probability, and so forth. You can also model locations of various sort. You can model orbits, cylinders. This is an example of modeling the trajectory of a UAV that takes off in this location, travels at a certain point, goes up, does an inspection over an area, then moves to another target area, does an inspection, comes down, and then returns back to its base. So all of these, complexities of where the device is, at which moment in time, following what trajectory, those can be captured in SEMs. Oh, well, so one thing I should mention, though, is that spectrum consortium models do not model terrain, and where appropriate terrain effects should be captured in the model's propagation and power map. So there has to be no dependence on external information issues. So that's part of the art of creating the SEM. Schedule. The schedule construct is used to identify the start and end time of a model. You can model periodic uses, duty cycles, and whatever type of say consistent or inconsistent operation in time that you may think of. So that was a quick overview of some of the constructs, but let's focus now on potential uses, potential ways in which these models can be used to enhance dynamic spectrum access. But before I get into that, so what must the models convey? Right? So the extent of RF emissions, right? What are the boundaries of RF emissions? A definition of what is interference, so what emissions from another user would be considered harmful. Time and location of use, are also important. And if known, behaviors and features that enable sharing. There's one construct, which I probably didn't focus on, called the protocol and policy construct, where you can say things like, oh yeah, these systems are going to operate in a listen before talk mode. Okay, so you can introduce that there, and then that could potentially allow for some additional sharing because of that type of behavior. So putting it all together, basically from the constructs, there's no, from the information in the construct, there's no real magic that's going to take place. You are just going to build a link computation, right? So a link margin or link budget computation. So you use the power mass, the reference power, the antenna radiation pattern. You compute the 1 meter power flux density out of the antenna. You use the propagation map to compute then the level of energy that will be coming from that antenna at the location of an intended receiver or entity or device against which you're trying to verify compatibility to see if that level of energy is going to exceed the threshold for allowable interference for this device. So the receiver here will take its reference power, its underlay mass, its antenna pattern, and compute the allowed power or spectral flux density of interference. And if it's below, sorry, so if the received energy is below that interference threshold, then the device this transmitter won't be interfering this receiver. If it's above the threshold, then it will be interfering. That's a very short way of describing the compatibility computation. There are some nuances on that, right? If the system is frequency hopping system or a direct spectrum system, there are other ways in which that computation takes place, considering duty cycles and things like that. So the general process of compute compatibility will be determine if the two systems will use spectrum that is common to both of them, and will they be operating at the same time around the same location. Once you know that there's the potential to interfere because of the previous characteristics, then one way to go about it is to determine the constraining point. So on which direction of the antenna will the transmitter be causing the highest level of interference towards the direction of the receiver or system to which you're trying to verify compatibility. So when you're doing this in a one-to-one fashion, well, it's rather simple. But when you're trying to do it against a system, one transmitter against many receivers or many transmitters interacting with a set of receivers, then things get complicated. And designing algorithms and optimization methods to do this computation rather fast is an interesting area of research. I should also mention that you can also use SEMs to compute aggregate interference effects. And there's a whole section in the standard that shows you how to do this. So then again, this goes into the discussions of allowing spectrum sharing, right? It's not just going to be one device against another device. It's going to be many devices against many other devices. So the better that you can find spectrum holes in an area or thresholds that allow you to put another device to also transmit and share spectrum in an area, those results are important. So it's going to be another benefit of using SEMs. If you go through the standard, you would see things like this. So just for a transmitter model, okay, you have to take into account all these constructs, and it'll tell you which tables to look at, and then those tables have more values that you have to provide, and some optional, some are mandatory. The more detailed you provide, the better you can use the better the boundaries that you're defining, and there are going to be issues there as to whether you're being truthful or not, but that's outside the standard. Again, it could be another area of research, and the ones I'm showing right now are for receivers. So from let's say, how does an SEM look? This is just one example using an XML-based schema for representing the data model mentioned in the standard. And so I'll just briefly showing there, and just showing the spectrum mask. It's a way longer document for an 802.11ac transmitter. I built some software tool. It's open source, but don't use it right now because I broke the code a couple of weeks ago. I'll update it. I'm sure. Just give me 2 or 3 weeks. So spectrum consortium model and builder analysis tool. We did use part of this code in some of the code that we that's implemented in the demo that I mentioned that will take place in a while. So you can get, actually this report results should be here, so you have a transmitter and this is the underlay mask of the receiver and say, oh yeah, you're really overlapping and the power margin 17 something. So if you brought down the transmit power of this transmitter by 17 dBs, 17.7 dBs, now you would be outside the interference threshold of the receiver. Well, that's just something that you can do. The tool also gives you a GUI to start building the models. Entities like MITRE have built other tools and model a lot of scenarios. So they've gone through modeling scenarios where the devices are moving across a wide geographic area, and they deconflict algorithmically and autonomously to say, well, yeah, I'm using this frequency given by this color. You're going to use this other frequency, so given by a different color, but so that we won't interfere. And this can take place as they're moving, and it because of the simplicity, of the tractability. I wouldn't say simplicity of the computations based on SCMs. This deconfliction can take place quite fast. So to finalize, I think I have like 2 or 3 minutes. Within IRIS, we've been looking at how we can incorporate SCMs in the protection of passive devices. So basically, the idea there is to have passive device. If you saw Marwan's presentation, use a database approach, right? But then that database will contain SCMs, right? So have passive devices declare their RF protection needs with SCMs, and this it helps introduce this concept of declarative, spectrum management. Some call it model-based spectrum management, right? Where instead of trying to find people scanning like crazy and trying to find where the interferers are, well, what if everybody just told you, within certain privacy concerns, what if the devices just told you where they are and how they're transmitting, so that you can avoid or share or agree on a sharing mechanism in a much more efficient way, and which would then in turn reduce the need for so much scanning, but again, coming back to the protection of passive devices, it'd be the passive device expressing their protection needs, and then some database collecting the SCMs and of potential interferers to say, yes, you can operate because right now this passive device is conducting an observation on these sets of frequencies which don't overlap with the ones you're operating, or the IF portion of the current observation is not overlapping with any of these and things like that, right? So SCMs for passive devices. SCMs can also be used potentially, again, another research area, in building spectrum license agreements, service level agreements or spectrum access agreements. So where entities specify their boundary spectrum use with SCMs, and then you put that in a whole agreement with other parameters that are negotiated. Okay, what happens if you violate the boundaries of your SCM? What's the probability that you go out of these boundaries? And if you go out, what are the fees? How do we monitor that takes place? There's a sensing component here that should be introduced. So there's a potential to put SCMs in enhancing policies and sharing agreements. So to finalize, just a couple of comments. So spectrum consensus models are a data model that can facilitate new spectrum management interactions. The idea again is to move, we think SCMs help us move towards a more declarative spectrum sharing, spectrum management framework, but sensing might also be needed. SCMs are standardized within IEEE 1900.5.2. Just to put in a shameless plug here, SCMs are not the only key work being conducted by this by the 1905 work group. We just finished work on a first version of a standard policy language for dynamic spectrum access systems. So the idea was to develop a language that also is machine readable, machine processable, and it uses SCMs as its native data construct. And we're currently making more enhancements to the standard. So some references, and with that, I don't know if I have time for questions, but thank you for your attention.